Hello learners, this is module 2 of unit 4 CA 8404 concrete technology course. In the first module we have seen properties of fresh concrete and the test to compute properties of fresh concrete. In this module we will be seeing the properties of hardened concrete and various tests to determine the properties of hardened concrete. So we will be seeing compressive strength, split tensile strength, flexural strength, stress strain curve of concrete, modulus of elasticity in this module. The first one is compressive strength of concrete. The compressive strength of concrete is defined as the strength of 28 years old specimens tested under monotonic uniaxial compressive load. This is done using compression testing machine. Testing of cylindrical samples with 15 cm diameter and 30 cm height is used if the cylindrical specimens are used. In India, normally the specimens are made in cube shape of having dimensions 15 cm. Normally, the compressive strength of concrete is determined by testing, and the tensile strength and modulus of elasticity are expressed in terms of the compressive strength. So, when you need tensile strength and modulus elasticity of concrete, most of the time we measure or we test for compressive strength of the concrete, and from the compressive strength of the concrete, in the code books, in the Indian standards, we have formulas to calculate tensile strength and modulus of elasticity from the compressive strength of the value. This compressive strength of the value at 28 days after after casting is taken as characteristic compressive strength of concrete. So the first figure is cylindrical specimen where the monotonic uniaxial compression is applied. The second figure is cube specimen. So normally the cylindrical specimen will have lower compressive strength when compared to cube specimen because of aspect ratio. Aspect ratio is due to the size and shape difference between the cylinder and cube. The cube takes more load compared to the cylindrical specimen. Approximately the cylinder strength is 0.85 times to 0.8 times of the cube strength. So in the next graph, the relative strength to height to diameter ratio is given. When the height to diameter or cross section is same, it carries maximum load. There are three types of failure modes for cylinders. Under axial compression, concrete fails in shear. The separation of the specimen into columnar pieces by what is known as splitting or columnar fracture. The third one is combination of both shear and splitting failure. So as you can see in the figure A, all the cracks occurs at an angle approximately 45 degree, whereas in splitting or columnar fracture, all the cracks are straight line. In the third figure, both 45 degree line crack and a straight line crack both occurs. So these are the three failure types of concrete under compressive force. So these are the practical situations where the compression of concrete is tested. The last figure is the compression testing machine. The next value is tensile strength of the concrete. The tensile strength of the concrete is calculated in three ways. One is a direct way and the other two is the indirect ways. The tensile strength of concrete is much lower than the compressive strength, largely because of the ease with which cracks can propagate under tensile loads. The tensile strength of concrete is measured in three ways: direct tension, splitting tension and flexural tension. So direct tension is the direct way of calculating the tensile strength of concrete, whereas the splitting tension and flexural tension are the indirect ways of calculating the tensile strength. So first one is the direct tension. It is very similar to the compression test. Instead of applying axial compression, here we are applying axial tension. The second is the flexural test. It is also called as modular rupture test. In this, when the concrete beam is made and is tested under flexural load. The third one is split cylinder test, whereas the concrete is casted into cylindrical specimen and a tensile load is applied along the diameter of the cylindrical specimen. It is difficult to test concrete in direct tension because of the problem of gripping the specimen satisfactorily and because there must be no eccentricity of the applied load. Therefore, direct tensile test is not standardized and are rarely used. Modulus of rupture test and splitting test are commonly used to determine the tensile strength of concrete. So this is the direct tension test, the most direct way of measuring the tensile strength. not a practically feasible test. This is the split tensile strength. As I already told, the cylinder is casted of dimension 15 centimeter diameter and 30 centimeter length, and the axial tensile load is applied along the one of the diameters, along the diameter. So the failure load P is noted, and the split tensile strength is calculated using the formula 2P divided by pi LD, where P is the failure at load. So these are the real life testing mission, and the first figure is the after applying the load, after the failure, the concrete, the cylindrical specimen looks like that. So modulus of rupture test. So as I told, the concrete is casted into beam, and it can be done in either ways. 4-point loading, 2 point loads can be applied, or 1 point load can be applied. So once the failure P is known, from there you can calculate from the formula tensile strength of the concrete is calculated using 6. The moment at which the failure occurs, B is the cross section, breadth of the rectangular section, and H is the height of the cross section. Relationship between compressive and tensile strength of concrete. The tensile strength of concrete is proportional to the square root of the compressive strength. The proportionality constant depends upon many factors such as the concrete strength and the test method used to determine the tensile strength. The following relations can be used as a rule of thumb. If you are testing it in a direct way, it may be 0.35 square root of FC, where FC is characteristic compressive strength. If you are testing the concrete in split tensile strength manner, the value will be coming around 0.5 times of square root of FCK. If you are testing the concrete in flexural tensile strength way, it will be, the concrete tensile strength will be 0.64 times of root over FCK. Normally, in IS 456-2000, the tensile strength of concrete is given as 0.7 root over FCK. 0.7 root over FCK. The next one is stress strain curve of concrete. The stress strain curve, once it is mainly obtained from compression testing machine. The load divided by the cross sectional area. If it is a cube specimen, the cross sectional area is 15 cm by 15 cm. So the load divided by area will be the stress, and the strain is calculated when you measure the deformation and the original length is known. So change in length divided by original length will give you strain. So once the load is applied, you calculate the stress and the corresponding strain, and the graph is plotted. You can see the stress strain curve of concrete at the bottom. At stress below 30% of ultimate strength, the transition zone cracks remain stable. The stress strain plot remains linear. So up to 30% of the ultimate load, the stress strain curve of the concrete remains linear. At stress between 30 to 50% of ultimate strength, the transition zone micro cracks begin to increase in length with and numbers. The stress strain plot becomes nonlinear. So after the load cross the 30% of the ultimate strength, the micro pores tends to get bigger and the number of micro cracks appears to be higher. At 50 to 60% of the ultimate stress, cracks begin to form in the matrix. With the further increase to about 75% of the ultimate stress, the cracks in the transition become unstable and the crack propagation in the matrix will increase. The stress strain curve bends towards the horizontal. At about 75 to 80% of the ultimate stress, the stress reaches a critical stress level for spontaneous crack growth under a sustained stress. Cracks propagate rapidly in both the matrix and the transition zone. Failure occurs when the cracks join together and become continuous, and the failure is sudden and brittle in nature. Concrete is not a truly elastic material as evident from the nonlinear stress strain curve. Since concrete is a nonlinear curve, the slope is not constant. For example, if you take the stress strain curve of steel, up to yield stress point, the stress strain curve is almost linear, so that if you take slope at any point, it will be same. Why we are taking slope is we need to find Young's modulus of the material. So if you take at any point, say for example, if you take at the initial stress strain stage up to 30 to 50% stress, it will have different modulus, and if you take it further from 50 to 60%, it will have different Young's modulus, and 60 to 80% it will be having different Young's modulus. So since the curve is nonlinear, it will be having n number of Young's modulus. You have to find a correct Young's modulus pertaining to the Young's modulus of concrete. So mainly three types of slopes modulus, tangent modulus are used. The initial tangent modulus is given by the slope of a line drawn tangent to the stress strain curve at the origin. So IT is the initial tangent curve. Here the tangent is drawn at the starting point, at the origin point, and the slope of this line is taken as the initial tangent modulus or Young's modulus of the concrete. The second is tangent modulus. It is given by the slope of a line drawn tangent to the stress strain curve at any point on the curve. So you are taking the curve. Normally the tangent modulus they do at 1/3 of the FCK, 1/3 of the ultimate failure. So anywhere at any point on the curve you draw a tangent and take the slope. It is the tangent modulus. And the final one is secant modulus. It is the combination of both initial tangent modulus and tangent modulus. The secant modulus is given by the slope of a line drawn from the origin to a point on the curve corresponding to a 40% stress of the failure stress. So here in the graph IT is initial tangent, tangent is given, and the last at the bottom you can find the secant. Here first you have to locate a point in the curve 40% corresponding to the 40% of the ultimate stress. Then you join the origin with the point you have chosen in the curve and connect a straight line. The slope of this straight line is called as secant modulus. Normally in RCC we are using secant modulus in determining the elastic modulus of concrete. Young's modulus of concrete. Apart from this, Young's modulus of concrete is calculated in a number of ways. Here one of the few ways are shown. Testing of cube or cylinder in uniaxial compression test. Measure load and the corresponding deformation. As the load is increased, draw the stress strain curve. Stresses we already know, load by area, or strain is change in length divided by original length. Use compressometer and extensometer to measure deformations. Draw stress strain diagram and determine the required modulus. Deflect. This is the first. That is, from uniaxial compression test, we are calculating stress strain, plotting the graph, and we are taking, using the curve, we are taking the modulus anywhere. You can take initial tangent modulus, or secant modulus. The slope of the corresponding line will give you the Young's modulus of the concrete. The next step is an indirect method where we are the concrete beam is subjected to flexural test and the deflection is noted. So for example, this is the deflection for simply supported central point load WLQ by 48 EA. So once you know the dimensions, you know the moment of inertia, you have to find the Young's modulus. This one we have to find. We know the load applied, we know the length, and we will, from using dial gauges or LVDT, you can easily calculate deflection. So in this formula, the only unknown is Young's modulus. So upon substituting all the known values, you can easily find Young's modulus. But this is an indirect way and holds good to in a certain conditions only. So relationship between modulus of elasticity and strength. Modulus of elasticity of concrete increases approximately with the square root of the strength. As we have seen in tensile strength value also, here both the tensile strength and Young's modulus depends upon compressive strength and both varies with respect to square root of FCK. According to IS 456-2000, the Young's modulus of elasticity is given as 5000 root over FCK. For example, if it is a 25 megapascal grade of concrete, FCK is 25. The Young's modulus of concrete for 25 megapascal concrete is square root of 25 is 5. So 5 into 5000, it is 25,000 Newton per mm square. 25,000 Newton per mm square. So as we have seen already, normally we don't do tests for calculating the tensile strength and Young's modulus of the concrete. We perform only compressive strength in the concrete, and once you know the FCK, concrete strength at 28 days after casting, with that FCK, we will be calculating tensile strength and Young's modulus using code given formula. For calculating the tensile strength, it is 0.7 square root of FCK, whereas for Young's modulus, it is 5000 root over FCK. Thank you.